Hello, and welcome to York's Observatory's TeleTube, the online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. TeleTube broadcasts on YouTube every Wednesday night at 7:30 local Toronto time. For any questions or comments you have of our past shows, or if you have suggestions for future topics, please send us an email at observe@yorku.ca. And you can also connect with us on Twitter or Instagram with the handle at York Observatory and Facebook at Alan I. Carswell Obs. I am Matt, and I'll be one of your hosts this evening, along with Obada, Shannon, and Amin, broadcasting from the LNI Carswell Observatory located in Toronto, Ontario, Canada. Tonight, we've got a great presentation about extreme cold environments in space. But before we get started with our main show, we want to give you a little update on what you can see this coming week. This week we have the Pleiades cluster as well as the moon, Procyon, Capella, which by the way is the sixth brightest star in the night sky, Betelgeuse, and the planet Mars, which will also be visible to the naked eye tonight. For tonight's presentation, we'll be talking about some of the extreme environments we can find in space and especially in our solar system. And we usually look up and wonder how it would feel like to be standing in one of these objects we can see lighting up in the night sky. But we don't actually realize that space and the celestial objects we can see there can have some of the most extreme environments we could ever imagine, hot or cold. One example of this is the moon, which we are able to see tonight. And tomorrow is actually a really important day for the moon because it's actually the wolf moon day. In case you're wondering what is it, it's basically the first full moon of the year or the first full moon in January. And it is called the wolf moon because for ancient cultures like the Native Americans and medieval Europeans, they called it the wolf moon because the wolves hold more at this time of the year as there was less food. It is also known as the old moon, the ice moon, the snow moon, and the moon after Yule for other cultures. But getting back to the theme of tonight's presentation, um, did you know that the daytime maximum temperatures of the moon are sensitive to the albedo of the moon's surface and can range from 387 to 397 Kelvin, which in Celsius is approximately 120 degrees in average. Meanwhile, the nighttime temperatures of the moon are sensitive to the thermophysical properties of the regolith. The regolith is a layer of unconsolidated debris and fragmented rocks on top of the lunar surface. And we don't call it soil because that is mostly defined as having organic content. Um, Even if the areas of regolith with high rock abundance are able to maintain a temperature of 50 Kelvin above the average, the temperature of the moon is at night. It's around 95 Kelvin or minus 173 Celsius. Now, taking account that the coldest temperature ever recorded on Earth was of minus 89 Celsius, and it was in Antarctica. So the moon can actually get pretty cold, colder than we can imagine, in fact. And something not that cold in the night sky, and that we hope in the near future to send a human there, is the planet Mars, which can also be colder than the coldest temperatures on Earth as well, but it can depend on the season. For example, the average temperature on Mars is minus 60 degrees Celsius, but during the Martian winter, temperatures can get as low as minus 125 degrees. So if you ever go to Mars, make sure to take your best and thickest space jacket as well as a cup of hot coffee and you'll be good to go. But for the moment, let's start with the definition of what and how do we measure temperatures in space. Some example of the coldest temperatures in the solar system, and a little bit more about these interesting and mysterious places full of wonder, amazing, and yet freaking freezing landscapes. Go ahead, Obara.
Thank you for the introduction, Ma. Hi, my name is Obada, and I'll begin the show tonight by giving a brief explanation of how we use temperatures to measure and understand objects in the universe, as well as the use and applications of such methods. Kelvin scale is an absolute temperature unit named after Lord Kelvin in the 19th century. Lord Kelvin was a British mathematician, physicist, and engineer. He was president of the Royal Society, a learned society in England and one of the oldest and most prominent in the world. The goal was to promote scientific discovery and experimentation, which is what led to the eventual success of Lord Kelvin's temperature scale, as well as the development of the first and second law of thermodynamics. Kelvin scale isn't as popular as the Celsius scale or the Fahrenheit scale, since it's not used in day-to-day practices. However, most scientists and engineers use Kelvin for many of their calculations and operations. Many of you are probably familiar with the fact that temperature is an average of the kinetic energy possessed by the molecules you're trying to measure the temperature of. Now, since a molecule could theoretically have zero kinetic energy, which means the molecule is at complete rest, that would be the starting point for the Kelvin scale. The point of zero kinetic energy is called absolute zero, or 0 K. It is not possible to have a negative temperature on the Kelvin scale, because of the fact that any given molecule, atom, or particle could not have a negative kinetic energy. Now, as I mentioned, it is almost impossible to reach absolute zero, since any small external energy source could push the certain molecule you're trying to measure the temperature of slightly above absolute zero. The Celsius scale is simply a shift of the Kelvin scale by 273.15 degrees. Absolute zero on the Celsius scale would be minus 273.15 degrees Celsius. Now, I'd like to mention there's no theoretical limit on how hot an object gets, so it is technically possible for an object in our universe to reach a trillion degrees or even a quadrillion degrees Kelvin. Now, you might be wondering, how is it possible to measure a temperature of an object that is millions of light years away? Certainly, the object of interest doesn't actually emit heat that we can detect here on Earth. The trick is to use blackbody radiators to determine the color temperature of the object. You might be familiar with this term, as it's used to measure the color temperature of light emitted from modern light bulbs. A blackbody radiator is a measure of electromagnetic radiation from an idealized, opaque, and non-reflective body. The term first appeared by Gustav Kirchhoff in the mid-19th century. The term is also called thermal radiation, temperature radiation, or cavity radiation. The concept depends on Planck's theory, which was developed by Max Planck in the year 1918. His theory essentially states that for any given frequency of light, there is a specific quantized energy associated with that photon. In other words, each light particle or photon has a discrete unit of energy that can be associated with a certain frequency. The frequency of light is what dictates its color, at least in the visible spectrum. Most light surrounding us is actually invisible to the human eye. Our eyes can only detect a frequency from about 380 to 750 Hz. Light like infrared, which we perceive as heat, can only be seen with special technological equipment. Infrared has a lower frequency, which means it has a lower energy or temperature. Ultraviolet, on the other hand, which is a slightly harmful light wave most commonly emitted from the sun, has a higher temperature and thus requires a hotter source for it to be emitted. From this, we could say that increasing the temperature of the source from which light is emitted will result in a higher frequency of light. This is the basis of blackbody radiation. We also can say that for all normal baryonic matter, which is a normal matter that we can see and observe, emits electromagnetic radiation if it is above absolute zero. The image on the right shows a spectral graph of the sun. By looking at where the line peaks, we can determine the temperature of the surface of the sun. Of course, this technique is not just limited to the sun. It can be used on planets, stars, and even distant galaxies. Before Amin and Shannon start talking about some of the extreme cold conditions here in the solar system, I'd like to give an example of an extremely cold nebula in our galaxy, and how it's essentially impossible for a naturally occurring material or object to fall below 1 degree Kelvin. The coldest object we have yet to discover is the Boomerang Nebula, pictured here on the left. It was discovered by astronomers in 1995 using the Swedish ESO submillimeter telescope. The nebula is located in the Centaurus constellation and is about 5,000 light years away. During observations, astronomers were able to record a temperature of minus 272 degrees Celsius or 1 degree Kelvin. Using the techniques we discussed earlier, the temperature is only 1 degree above absolute zero, and it is the coldest place in the universe aside from laboratory-created conditions, which have reached temperatures as low as 1 nanokelvin. That's insanely cold. And what's especially unique about this nebula is its ability to somehow stay warmer than the temperature of space itself. The coldest an area of distant and very empty space can get is minus 270 Kelvin, which is the temperature of the cosmic microwave background. The cosmic microwave background, or CMB for short, is the background radiation of the universe, emitted during the Big Bang, present all around us despite being 13.7 billion years old. and it is able to emit enough radiation to keep the coldest parts of space 3 degrees warmer than absolute zero. One study claims that the reason the nebula is able to reach such temperatures is because the way the Boomerang Nebula expels unusually high ultra-cold gas from its center, enveloping the center edges. The dying star at the heart of the nebula is shedding its mass at an unusually high rate, which is the reason for the fierce cold winds being blown away from the center. It is also the reason for the bow tie-like shape. The wind creates a sort of refrigeration effect that is able to seal off the cold parts of the nebula in the cosmic microwave background. Now, Amin will be talking about some of the cold temperatures present in the gas giants here in our solar system.
The solar system and its contents were all created from the same accumulation of matter. Most of it went into the sun, but other parts of the matter cloud became the planets, comets, meteors, and other objects. Once the sun had enough mass, intense pressure resulted in its core, and nuclear fusion could begin there. This made the sun light up for the first time. Pressure from this light, called radiation pressure, and from the solar wind, which is a stream of particles that the sun emits, pushed the remaining matter away. The heavier terrestrial planets, which are mainly rocky, remain relatively near the sun. These planets are Mercury, Venus, our own Earth, and Mars. The lighter gaseous planets were pushed further back and became the gas giants. These planets are Jupiter, Saturn, Uranus, and Neptune. There's an important boundary in the solar system called the ice line or frost line. Beyond this line, water, ammonia, methane, carbon dioxide, and carbon monoxide can condense into ice. The gas giants are able to retain the gaseous and volatile materials which the terrestrial planets could not hold onto due to their size. These gases are mainly hydrogen and helium, with some heavier gases as well. The gas giants are often called failed stars because they contain the same materials as stars, but were too small to have nuclear fusion start. The gas giants have several layers. The outer layers consist of mainly hydrogen and helium gas, with water and ammonia clouds, and also liquid hydrogen deeper in. These layers are quite cold, even in Jupiter and Saturn, which may surprise some of you, as there are many ravaging storms at this level, including gigantic ones like the Great Red Spot on Jupiter. Jupiter actually has a surface temperature of negative 161 degrees Celsius. Saturn is at negative 189 degrees, Uranus has negative 220 degrees, and finally Neptune has an outer temperature of negative 218 degrees Celsius. These are only estimates, and the temperatures vary over time and location on the surface of the planet. Uranus and Neptune have heavier materials than Jupiter and Saturn, which we call ices. Ices can form there because of the greater distance from the sun. Under the outer layers of the gas giants, there's a large layer of metallic hydrogen. There's enough pressure here for hydrogen to condense into metallic form. This metallic layer rotates with the planet and can generate a strong magnetic field. At the very center of the gas giants, we believe that there is a small rocky core made up of heavier elements. As you get closer to this core, the temperature should increase. At the core itself, the temperature must be at several thousands of degrees Kelvin. Due to the difficulty in penetrating the outer layers, we do not know much about the cores. Jupiter is the first of the gas giants, starting from the sun and counting outward. It is the largest planet in the solar system and has a mass of 1.9 times 10 to the 27 kilograms, which is 318 Earths, and a radius of 70,000 kilometers, which is 11 times wider than Earth. If Earth were a nickel, Jupiter would be the size of a basketball. The mass of Jupiter is 2.5 times the mass of all the other planets combined. The majority of the mass is hydrogen, with helium being a quarter of it. The colorful stripes and swirls you can see at the surface are cold and windy clouds made of water and ammonia. The color comes from sulfur, phosphorus, and similar elements. The fast rotation of Jupiter causes strong streams of gas, creating the visible belts. The Great Red Spot is a defining feature, and it is a megastorm which has been raging for hundreds of years. Like the other gas giants, there's no well-defined surface. There's only gas which gets denser and denser as you go further down. We define the surface as the point where the atmospheric pressure is equal to that of Earth. Eventually, the pressure causes hydrogen to become a liquid and then metallic. Jupiter has 4 large moons: Io, Europa, Ganymede, and Callisto. There are dozens of other smaller moons as well. Europa is a particularly cold moon with a water ice crust. Under the ice, there may be liquid water and there's a potential for the existence of life. The surface temperature of Europa ranges from negative 134 degrees to negative 223 degrees. The next gas giant is Saturn. It is also next in line from Jupiter in terms of size. Saturn's mass is 5.7 times 10 to the 26 kilograms, which is 95 Earths. The radius is 58,000 kilometers, and the volume is 764 Earths. Because the volume is so large but the mass is relatively low, Saturn has a very low density, and is even lower than that of water by 30%. As with the other gas giants, the outer layer is gaseous with hydrogen and helium, and the hydrogen becomes liquid and metallic further inward. The yellowish color comes from ammonia crystals in the upper atmosphere. The most striking feature is the ring system. All the gas giants have rings, but Saturn has the most prominent and visible rings of them all. The rings are composed of water ice with some impurities and a carbon coating. The particle size ranges from specks of dust up to large rocks with 10-meter diameters. Starting at 6,600 kilometers from the surface of Saturn, the rings extend for over 100,000 kilometers, but the thickness is quite low, at only 20 meters. Depending on how the rings align with the line of sight, we sometimes can't even see them if they are viewed edge-on. Saturn also has dozens of moons, with Titan being the largest. Titan is another cold place in the solar system, with a temperature of negative 149.5 degrees Celsius. It is made up of ice and rock, with rock in the core surrounded by layers of thick ice. At this point in the solar system, things are beginning to get colder, and ice is more pervasive. After Saturn comes Uranus. Uranus and Neptune are classified separately from Jupiter and Saturn, and they're called the ice giants. Uranus has a mass of 8.7 times 10 to the 25 kilograms, or 14.5 Earths, making it the least massive gas giant. The radius is 25,000 kilometers, and the volume is 63 Earths. The ice giants, including Uranus, also have hydrogen and helium gas in the atmosphere, but they also contain more ices, such as water ice, methane ice, and ammonia ice. There are also some trace hydrocarbons, which are also known as organic compounds. Uranus has the coldest atmosphere in the solar system. There's a layer structure of clouds, with methane in the upper layers and water below that. The wind speed in the clouds is quite large, at 250 meters per second. The interior of the planet is probably made up of rock and also ices. Like the other gas giants, Uranus has rings, a magnetic field, and several moons. Uranus has an interesting feature in that it is tilted sideways compared to the other planets. It's possible that something struck Uranus at some point in its history, causing the tilt in the axis of rotation. Under the atmosphere, there is a mantle made up of ice. The core is rocky with silicates, iron, and nickel probably present, but is a quite small core, like the other gas giants. Uranus has rings, but they have smaller particles than the rings of Saturn, and they're extremely narrow, so they're hard to spot. The moons of Uranus are all dark-colored and rocky and also icy again. They are made up of approximately equal amounts of ice and rock, but the moon Miranda is mostly ice alone. The final gas giant is Neptune, which is also an ice giant. It has a mass of 10 to the 26 kilograms, or 17 Earths. The radius is 25,000 kilometers, and the volume is 58 Earths. Neptune is the most dense of the gas giants. Although it is more massive than Uranus, it is actually smaller in diameter because the extra mass causes compression of the atmosphere. The layers of Neptune are very similar to that of Uranus. There are gases in the outer layers, followed by ice, followed by a rocky and icy core. The atmosphere is 80% hydrogen and 19% helium. There's also a little bit of methane. Neptune's spectra suggests that its lower stratosphere is hazy due to condensation of particles of ultraviolet photolysis of methane, such as ethane and ethine. The stratosphere is also home to trace amounts of carbon monoxide and hydrogen cyanide. The stratosphere of Neptune is warmer than that of Uranus due to the elevated concentration of hydrocarbons. Neptune is the windiest planet in the solar system, with wind speeds of more than 2,000 kilometers an hour. There's a magnetic field, several moons, and rings. The largest moon is Triton, which is not to be confused with Saturn's moon Titan. Triton is the only large moon in the solar system to orbit its planet in the opposite direction than the other moons. As with most objects this far from the sun, it is a very cold place, with a temperature of negative 235.2 degrees Celsius.
Thank you, Amin. Uranus and Neptune are certainly very interesting. Uranus and Neptune, however, are not the only planetary objects in our solar system that exhibit extreme cold environments. What used to be known as a planet, but is now known as the most famous dwarf planet, Pluto. Named after the Roman god of the underworld, Pluto is a very special object in our solar system and is the farthest planetary object away from the Sun. More precisely, Pluto is 5.915 times 10 to the power of 9 kilometers away from the Sun. As Obada previously mentioned, spectroscopy can be used to detect celestial objects. Pluto was discovered on February 18, 1930, by Clyde W. Tombaugh, who worked at Lowell Observatory. The discovery of Pluto was a result of using mathematics and spectroscopy. Similar to Uranus and Neptune's moon, Pluto is composed of rock ice material, and its surface is a combination of carbon dioxide ice, nitrogen ice, and methane ice. Scientists theorize that Pluto has 3 layers, the core being made of silicate to an ice-water crust. Sandwiched between these 2 layers is a liquid water ocean. An image of this is seen on the left of the slide. Pluto is small when compared to other planets in the solar system. Pluto has a diameter of 2,300 kilometers and a mass of 1.3 to the power of 10 to the power of 22 kilograms. Therefore, is 1/6 the size of Earth. Pluto actually has 5 moons: Charon, Styx, Nix, Erebos, and Hydra. An image is seen on the right of the slide. As you can see, the moon Charon is much larger than the rest. Pluto has a surface filled with craters, mountains, and valleys, with temperatures ranging from -226 to -240 degrees Celsius. Brr, that's cold. The origin of Pluto seems to still puzzle astronomers, but it's theorized that Pluto may have been formed due to a collection of several comets and objects in the Kuiper belt. As I mentioned earlier, Pluto has a very low temperature and is the coldest when compared to other planets in the solar system. The hydrocarbon particles which are present in Pluto's atmosphere is what is the cause of such low temperatures. Through modeling, it was predicted that based on the atmosphere of Pluto, that the average temperature would be around -170 degrees Celsius. However, in July 2015, NASA's New Horizons spacecraft measured that Pluto's temperature was actually 30 degrees lower than the modeled prediction. Scientists and astronomers alike truly wondered how a discrepancy like such could happen. NASA's New Horizons spacecraft allowed for there to be more knowledge on Pluto, and it spotted new information about Pluto that was not known before. For example, it noticed a layer of haze that was present above the planet. This haze is most likely due to the chemical reactions that occur in the upper atmosphere of Pluto. These chemical reactions occur when the sun's ultraviolet rays come in contact with the nitrogen and methane in the atmosphere to form hydrocarbon particles. Pluto is not the only planetary object that has dealt with this reaction. Titan, Saturn's biggest moon, has a similar haze that is so thick that it can be difficult to see the surface of the moon. Pluto's haze can efficiently absorb solar energy, yet it emits majority of this energy back into space in the form of heat, infrared radiation. However, even though scientists and astronomers seem to have a fair knowledge on Pluto, there's not a complete understanding of its temperature. Maybe in the future there'll be more observations on Pluto. Pluto's hazes radiate a lot of heat into space. A telescope such as the James Webb Space Telescope, which launched in 2019, should be able to detect it. As mentioned earlier, Pluto has 5 moons. The largest of these moons, and by far the most interesting, Charon. The moon Charon is named after the ferryman of Hades in Roman mythology. Charon is so large in comparison to Pluto that the pair is sometimes considered to be a binary planet system. The moon was discovered by James Christie, an astronomer at the Naval Observatory in Washington, D.C. in 1978. Amazingly, the moon takes the same amount of time to orbit Pluto as how long it takes for Pluto to rotate once, which is 6.4 days. The two planets are in a way locked together as they permanently face each other. Pluto and Charon are not that different in terms of size. Charon is only half the size of Pluto. With this, the system between Charon and Pluto is unique to the solar system, as it's the only binary planet system that exists in the solar system. Scientists use this example to further understand the physics and the dynamics behind the formation of binary systems, such as binary star systems. Scientists theorize that the formation of Pluto and Charon most likely occurred due to their collision and the remaining debris. Evident to the left image on the slide, you may notice that there's a red spot on the northern pole of the moon. It is due to emission of Pluto's atmosphere that was captured by Charon. Charon is not large enough to have its own atmosphere, therefore the moon is very cold. The temperature range from negative 258 degrees Celsius to negative 23 degrees Celsius. Charon is so cold that it's predicted through research that any gas that reaches Charon will freeze on the surface and turn to a solid, completely skipping over the liquid state. The moon is made up of ice, which is why it is a grayish white. The surface appears to be older than Pluto because Charon has much more craters on its surface. Now, what makes Charon so special? Charon has a single mountain on the moon, known as a mountain in the moat, a canyon that has a length of 1,600 kilometers, which is 4 times the size of the Grand Canyon. And south of this canyon lies a large smooth plain, known as the Vulcan Planum. The Vulcan Planum is the smoothest part of the moon, and researchers believe that this is due to cold volcanic activity known as cryovolcanism, which is a volcano that has a water-based lava. Now, Charon is pretty amazing. Let's not forget about its pair, Pluto. Pluto has inverse snow. Now, you may be wondering what that means. Well, allow me to explain. On Earth, the higher you go, the colder it gets. This is why large mountains have tops covered in snow. However, due to solar radiation, Pluto has a temperature inverse, where the higher you go, the warmer it gets. So that begs the question, why is there still snow and frost on Pluto? New Horizons found snow on Pluto, located near Pluto's equator. Yet the snow is nowhere similar to Earth's. Instead of being made of frozen water, Pluto's snow is actually made of frozen methane. So how does the methane snow end up on the mountains? If as the air rises, it warms up. Researchers use a climate model to figure out that Pluto's atmosphere is actually made up primarily of nitrogen, with a small amount of methane and carbon monoxide. Therefore, this research did not explain why there was snow in the mountains, as the atmosphere only had a small amount of methane. Further researching led to the answer. Methane was actually more concentrated at higher altitudes. That's why the only tops of the mountains had snow, and the lower altitudes did not. Pluto and its moons are so complex. Before the New Horizons flyby over Charon and Pluto, we did not know of this complexity. This research is only the beginning. The mission is only the beginning, and we have so much to learn and discover. Well, everyone, you've been listening to the L&I Carswell Observatory's weekly TeleTube broadcast, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Amin, Matt, Obada, and myself, Shannon. Make sure to leave any comments or questions in the comments section of this video and talk to us in the chat right now. We'll be around for the next 20 minutes to answer your questions. All of our programs are free, but if you would like to make a donation, see our website, observatory.info.yorku.ca. You can always connect with us on Twitter with the handle @YorkObservatory, and check out our website for show notes, content, updates, and contact information at observatory.info.yorku.ca. Thanks for tuning in, clear skies, and have a good night.